All right, everyone, let's take a little bit of a review of what we did yesterday with electromagnetic radiation. Who could tell me what electromagnetic radiation, or sometimes we just call it EMR, electromagnetic radiation, what it is? What does it consist of? One sentence or less. What does electromagnetic radiation consist of? What is it? Okay, it does consist of alternating electric and magnetic fields, yes? Or let's say changing electric and magnetic fields. Okay, what else? What else do we know about electromagnetic radiation? What is it? What does it consist of? How it's produced? So much for the one sentence or less. I'm going to change the question now to tell me everything you know about it in as many sentences as you need. It consists of changing electric and magnetic fields, and those electric and magnetic fields go like this, right? They're in what form? Sinusoidal waves, so they're in wave-like form. I'm going to say wave times 2 because there's an electric field wave and there's a magnetic field wave. What do we know about the orientation of that electric and magnetic field? They're perpendicular to each other. Just like just about everything in magnetism, perpendicular rears its head again. Okay? The electric field and the magnetic field are perpendicular to each other, and the direction of motion of these electromagnetic waves, both these electric and magnetic field waves, are going to be perpendicular to both of those waves. Okay, what else do we know about it? Here's what it consists of. Two electric and magnetic fields, they're waves, sinusoidal waves. They're perpendicular to each other and perpendicular to the way the wave moves. What causes it? What causes EMR, electromagnetic radiation? Go ahead, Spencer. Accelerating charged particles. If we have a moving charged particle, does that generate a magnetic field? A charged particle moving at a constant speed, that is. Does that generate a magnetic field? Sure it does. A charged particle that's moving at a constant speed absolutely generates a magnetic field. We learned about that early on in our last unit, right? Does it generate an electric field? Yes. So why does a charged particle moving at a constant velocity not generate electromagnetic radiation? What's the difference between the electric and the magnetic fields generated by the charged particle moving at a constant speed versus the charged particle that's accelerating? Tough crowd this morning. The charged particle that's moving at a constant speed generates a constant electric field. The charged particle that's moving at a constant speed generates a constant magnetic field. The charged particle that's accelerating generates a changing electric and a changing magnetic field. Why is that important? Why is it important that we get the changing electric and magnetic fields as opposed to just the constant value of electric and magnetic fields? Tristan? Yes, yes. The whole idea of this propagating, this self-propagating electromagnetic radiation, this way of carrying energy from one place to the other without the need for a medium, requires the electric field to produce magnetic field and the magnetic field to produce electric field. In order to get that happening, these fields have got to be changing. You can have a constant electric field and a constant magnetic field. That's great. They're not going to go anywhere. If you have a changing electric field and a changing magnetic field, then one produces the other produces the other produces the other, and so on, so that it propagates, it moves from one place to the other. That's how, when we turn on the light switch, light goes from the light bulb up there to our eyes, because the electric field that it produced and the magnetic field it produced were changing, which allowed the wave to be produced more and more and more as it went out further and further and further from the source. What happens to the part of the wave that produced the new part? Well, unless there's something there to replace it, it disappears, right? It's gone. The energy moves along with the wave. The only way that we can keep a continuous wave is if we have this constantly accelerating charged particle to basically produce more wave to take the place of the part of the wave that was just, in a sense, destroyed as it produced more. Does that make some sense? All right. All right. Who can tell me who it was that first experimentally verified Maxwell's theory of EMR? A, that accelerating charged particles generate EMR, and B, that EMR consists of changing electric and magnetic fields. Who was it? Hertz. It was Hertz. And he used an apparatus called the spark gap apparatus to do that. It consisted of a transformer. The transformer consists of a piece of iron or a piece of steel. On one side of it, you got a few wraps of wire, a few coils of wire wrapped around it with an AC power supply. On the other side, you've got more wraps of wire, more turns of wire wrapped around it. It's what we call a step-up transformer. It changes the potential difference from a low value to a higher value. Why do we want a higher value over here on the secondary side? Why is that important? Why couldn't we have just used the potential difference that we started with? The low value of potential difference. Yeah? Good. We want the charge to be able to jump across the gap. Okay, if we have a low potential difference, the electron is just going to sit where it is. It's not going to go anywhere. It's not going to jump that gap. Because there's no wire there, right? There's resistance there. If we have a big enough potential difference, the electron will jump the gap. As it jumps the gap, it must do what? It must accelerate. That's a physical thing. There's no new physics to that. Okay? There's no new theory to that. Okay? If a charged particle is at rest and then it's moving, it must accelerate in the process to get it moving. Okay? Newton could have told us that back in the 1600s. But now we know that if we can detect electromagnetic radiation over here in this little antenna, then it must have been caused by that accelerating charged particle. And if we detect EMR there, then we know that EMR must consist of a changing electric and magnetic field, because that's the only way that we're actually going to detect anything. The way this antenna works is that a changing magnetic field will produce an electric current in here. So if we detect a current, there must have been a changing magnetic field. And because the only thing that's different about this is that we have an accelerating charged particle, it must have been caused by the accelerating charged particle. Okay? It worked. It worked. Hertz fires this thing up. All of a sudden, we get an electric current induced over here. I don't know which way it would go. Doesn't really matter. Okay, we get an electric current induced there. Okay, that tells us that, in fact, electromagnetic radiation was there. Tells us that there must have been a magnetic field that was changing present, and it must have been caused by an accelerating charged particle. You guys remember the type of EMR that was discovered by Hertz? Or that was used by Hertz? Radio waves. Radio waves. Every time I mention one type of electromagnetic radiation, Daxon starts singing that song. That's good. That's good. If it's stuck in your head, Daxon, then there's no way that you're going to forget the order of these types of electromagnetic radiation, right? Okay. Whether we go by the song or whether we go by just some logic and a little bit of remembering, we can get this, right? In terms of frequency, let's start off with visible light. It goes in the middle. In terms of frequency, visible light consists of red first. Red is the lowest frequency of visible light. Then we've got orange, yellow, green, blue, indigo, and violet. What's below red? Infrared. What's above violet? Ultraviolet, right. What's the first type of EMR that was ever discovered? Radio waves. Well, it's got to be the simplest kind, so let's put this way down here on the far left. Well, I'll tell you what. Radar waves would be included with radio waves, and when you're rating the enemy, you want to avoid radar. So, come on. Come on. Radio waves. All right, what do we got left? We got microwaves, we got X-rays, we got gamma rays. Which one sounds the most dangerous? Gamma rays sounds the most dangerous. And to be honest, in many cases, it is the most dangerous. Okay, we got X-rays, we got microwaves. Which one sounds the next worst? Probably X-rays. Although microwaves have the potential to be dangerous as well, for a different reason. Gamma rays and X-rays are ionizing radiation. Gamma rays and X-rays, if inside your body will ionize atoms inside your body. They'll turn atoms into ions, turn atoms into charged particles. That's not supposed to happen. We don't want that. We don't want these little charged particles floating around inside our bodies, because then we get chemical reactions taking place inside our bodies that aren't supposed to happen. That can lead to all kinds of things. You could get sick. You could get cancer. You could die within hours, depending upon what your exposure is. So obviously, those two types of radiation are bad because they ionize atoms inside your body. Microwaves, people say, oh, microwaves, oh, they're bad for you. I've heard they're really, really bad for you, for a completely different reason. It's debatable whether they're even bad for you in reasonable quantities. But if they are even dangerous, it's for a completely different reason. Microwaves, your microwave oven uses microwaves. It doesn't seem to hurt you. Okay, your cell phone uses microwaves. Doesn't seem to really hurt you. Okay, although there is some debate about that, whether cell phones are actually somewhat dangerous or not. For the most part, I think consensus is that they're not. Okay. How can they potentially be dangerous? Well, microwaves have a frequency that corresponds to the resonant frequency of water. Water, that's the way microwave ovens work, right? Microwaves cause water molecules in your food to vibrate back and forth. It's resonance, right? The phenomenon of resonance that you learned about in Physics 20, just not in the context of cooking food. Causes the water molecules to vibrate. Vibrating water molecules generates what? Heat, right? That's what thermal energy is, right? Is vibrating molecules. So if we've got heat on the outside of this frozen whatever that you're trying to cook in the microwave oven, that heat will conduct to the inner part of it and cook the food. Now, sometimes, you cook it and it's like, oh, the outside is burnt and the inside is still frozen. Well, that's because it didn't conduct heat very well from the outside to the inside. Microwaves don't penetrate very far. They don't go to the inside of the food. It relies on conduction, old-fashioned conduction, to cook the inside of the food. Okay? It cooks the outside by this resonance phenomenon. X-rays and gamma rays, on the other hand, would easily penetrate to the inside of the food. But it would blast your food, but it wouldn't cook it. Okay, think about why it wouldn't cook it. Because the resonant frequency of water isn't in the range of X-rays and gamma rays. So it would go to the inside, but it wouldn't cook it, because you wouldn't cause the water molecules to vibrate. Does that make sense? Now, why can microwaves be potentially dangerous? Well, because they can cause water molecules to vibrate. Theoretically, if you're exposed to enough microwaves, you can cause water molecules inside your body to vibrate and generate heat. And all of a sudden, steam starts coming out of your head or something. I don't know. I don't know what the consequences of that would be, to be honest, but you can see how potentially that it could be dangerous. Your cell phones use such a low power of microwaves that it's probably not an issue, although there is some debate in the scientific community as to whether it is an issue or not. Just don't keep them in your pockets. Just don't keep them in your front pockets. That's all I can say. All right? Think about the other kinds of electromagnetic radiation. Are they dangerous? Visible light, that's not dangerous, right? Why do we wear sunglasses? Well, we actually wear sunglasses not to protect you from visible light, to protect you from ultraviolet, which can be dangerous, right? It can cause damage to the eyes. It can cause sunburns. Visible light can be dangerous if you have too much of it. My father was a mechanic while he worked in his working days, and as part of that, he welded. Well, the one thing he'd never let me do, never let me watch when he was working on something, was welding. Why not? Because the light is so bright. You have to wear these really good, basically really good sunglasses, although it's a welding mask, to protect your eyes and to protect your face from, burning pieces of metal as well, but to protect your eyes from the really, really bright light. Really, really bright light can affect you, can hurt you, right? So essentially, all of these types of EMR, in one way or another, have the potential to be dangerous. We're just saying that they're dangerous for different reasons and in varying amounts. All right, let's look at the different frequencies of these types of EMR. Remember that we don't have to memorize all 7 different frequency ranges. If we memorize 3, we should be good to go for the rest of them. Visible light, we'll go with that one first, because that's the one you have to be the most precise on. Okay, the other ones we need an order of magnitude. For visible light, we need actual numbers. Visible light was 4 times 10 to the 14 to 7.5 times 10 to the 14. That's the hardest one to remember because you've got to remember those base numbers. 4 to 7.5 times 10 to the 14 hertz. Anybody remember what microwaves were? 10 to the what? 10 to the 9 to, good, 10 to the 9 to 10 to the 12 hertz. X-rays were 10 to the 17 to 10 to the 20 hertz. Okay, if you're given a frequency that's 10 to the 22 hertz, what is it? Gamma rays. If you're given a frequency that's 10 to the 11 hertz, what is it? Microwaves. If you're given a frequency that's 10 to the 7 hertz, what is it? Radio waves. Make sense? What if you were given a wavelength? Let's say we were given a wavelength of 3 times 10 to the minus 8 meters. 3 times 10 to the minus 8 meters. How would we find out what kind of EMR that is? We never memorized any kind of wavelength range. So how would we figure that out? Yeah, let's get the frequency. Let's say frequency is equal to V over lambda. What is V, by the way? Speed of light. EMR is light. It's just 6 of the 7 kinds are light that we can't see, right? But it's all light. The speed of light is always 3 times 10 to the 8 in a vacuum. Divided by the wavelength here, which is 3 times 10 to the negative 8 meters, and that's going to give me 1.0 times 10 to the 16 hertz. What kind of EMR is this? It's ultraviolet. So you can see here actually, remember we did an example yesterday? The wavelength was 6 times 10 to the minus 7 meters, and that was visible light. We can see here that as we go from left to right in terms of frequency, the values increase. When we go from left to right in terms of wavelength, the values decrease. Notice when we go from visible light to ultraviolet, we're going to a smaller number for wavelength, a bigger negative exponent or a smaller number. Make sense? All right. I have written down here that we're going to have ourselves a quiz tomorrow on this stuff, but we'll wait until we check over the homework on page 647. So we'll make that quiz on Monday instead. Okay? Quiz on Monday on this stuff instead. Just make a note of that. And make sure you have those questions done tomorrow so that we can check them over and address any issues that you have with them. Yep. Is infrared harmful? Okay. Well, is infrared harmful? Okay. It's a good question. What is infrared radiation? It's heat. Is heat harmful? It depends. It depends. We're all exposed to infrared radiation right now. I laugh when I see, like, you know, marketing, right? You see some kind of product that, you know, it's a space heater and it says infrared space heater. No kidding. Like, no kidding. No, it's an X-ray space heater. Like, of course it's an infrared space heater. Like, you know, it's all marketing. Like, an infrared space heater doesn't normally hurt us, right? It's not normally dangerous. I've got one that's, you walk into Costco and they've got that parabolic one. It's great. Like, it generates a lot of heat. Although it's over a fairly focused area, so it's not going to heat a whole room. But, you know, if there's a cold area and you're there doing something, it's great. If you're working on something in the garage or whatever, it really is great. But it's got a little alarm if it gets kicked over. If a kid knocks it over, if your pet knocks it over, whatever, an alarm goes off on it. Okay, this buzzer sounds on it. Why? Yeah. So is it dangerous when used the way it's supposed to be used? No. That infrared radiation warms us up, and that's a good thing, right? Can it potentially be dangerous? Well, if it gets knocked over, maybe it could cause a fire. If it's too hot, you know, maybe it burns us. So infrared radiation could be dangerous, not at all in the same way as X-rays or gamma rays would be, or not even the same way as microwaves would be, or visible light or ultraviolet would be. But no, definitely not. You're not going to get cancer from infrared radiation. You might get burned from infrared radiation, right? You're not going to get cancer from visible light. You might wreck your eyes with visible light, right? Okay. Each of these have the potential to be dangerous in different circumstances, but it doesn't mean that they're automatically dangerous. X-rays, ionizing radiation, right? It's bad, ionizing radiation. Yeah, well, my son went for an X-ray on his foot here last week. He went for an X-ray at the dentist here 2 days ago. Is that bad? It does damage to his healthy cells? Sure it does. But he's young and he's healthy and his body repairs itself quicker than the damage is done. So in the end, a couple of X-rays in a couple of weeks isn't really going to hurt him, right? If he went for 5 X-rays a day for 6 weeks, would that hurt him? Yes, because his body wouldn't be that good at repairing itself. The damage would be done quicker than his body could repair itself. So, there's benefits and cons, pros and cons to each of these things. Each of them can be dangerous, or each of them can be safe, depending upon context, right? Even gamma rays, right? What are gamma rays used for oftentimes? Treatment of cancer. Okay, when probably everybody in this room has known somebody that has had radiation therapy for cancer. Chemotherapy is a concoction of chemicals. Okay, so it's a chemistry thing. Radiation therapy is gamma radiation. They use nuclear reactions at a hospital. Nuclear reactions at a hospital generate gamma rays, and they zap the tumor with gamma rays. And the idea is, hopefully, they obliterate that tumor. Okay? So that's a positive thing, right? That's a benefit of it. Okay? But obviously, it can also cause damage as well. All right. Let's look at the speed of electromagnetic radiation. We said yesterday that the speed of EMR is 3 times 10 to the 8 meters per second. Okay, we know that it's around 3.0 times 10 to the 8 meters per second in a vacuum. How do we know that? How do we know that? Let's go back a few centuries to a guy named Galileo. Everybody's heard of Galileo, right? Everybody knows Galileo. Galileo thought, hey, I'm a smart guy. I can find the speed of light. I got this great idea. Galileo said to his assistant, you stand over on that hill over here. We'll call it Hill B. I'm going to stand over here on this hill A. They're quite a distance apart, 1 kilometer or 2 apart. I'm going to stand there with a lamp. Okay? That lamp is going to be covered up with a piece of cloth so that you can't see that lamp. Okay? You're going to be standing over here with another lamp. It's going to be covered up with a cloth. So I'm not going to be able to see your lamp. You're not going to be able to see my lamp. Why are we standing on opposite hills then? Well, what's going to happen is Galileo is going to uncover his lamp. When Galileo uncovers his lamp, the light starts moving towards the guy on the second hill, Hill B. When the guy on Hill B sees the light, what does he do? He uncovers his lamp. Then that light starts traveling this way towards Galileo. Galileo is timing it. Galileo stops his little timer when he sees the light of his assistant. Why didn't the other guy just time it? Why didn't Galileo just uncover his lamp and then the other guy on Hill B just time it? How does he know when the light started, right? Isn't that kind of ingenious? Here's a neat little way of establishing when the light started and when it finished. Galileo starts and stops this whole thing. Okay, he uncovers it. Well, he knows right away when he uncovers it, he starts his little stopwatch. This guy over here, when he sees it, when the light travels that far, he sees it, he uncovers his. Okay, the light goes back this way. Galileo stops his little stopwatch. I don't know exactly. I say stopwatch. Of course, he didn't actually have a stopwatch. I'm not sure what he used to actually time it. And we'll just assume that he was able to time it. He gets a time. Well, he knows a distance. This is easy then, right? If he's got a time and he's got a distance, then he can simply use the equation V is equal to delta D over delta T in order to find the speed, right? What's the problem with this? Jack, what's the problem with this? No, it's not. It's not very accurate. In fact, that's the problem, right? That's essentially the answer to the question that I'm asking is it's not accurate, not at all. Why isn't it accurate, though? Why isn't it accurate, George? Yeah. Oh, there's a gigantic amount of human error here. So much more. Just human reaction time on a stopwatch is much greater than the time that it would take to go there and back. Remember what we said yesterday? Light would travel about 25 return trips across Canada in 1 second. If it travels that fast, right, the time that it takes it to travel a couple kilometers is minuscule compared to the time that it takes you to start and stop a stopwatch and uncover 2 lamps in the process. Right? Even if you got a number that was pretty good, that was close to the accepted value, it would be purely by luck. There wouldn't be any scientific validity to it whatsoever, even if you did get a good number. This just doesn't work. Human reaction time is just much too great. Does that make sense? So why do we do this? Why do we talk about this then? Well, in a minute we're going to talk about a much better method for finding the speed of light. And I want you to be able to distinguish between 2 methods. One that's not such a good method for finding the speed of light, although kind of a neat idea. It just doesn't work because of human reaction time. And then a much better method for finding the speed of light. Be able to distinguish between what's good and what's not. What's reasonably accurate, what gives you good results, and what gives you poor results. All right, write this down, and then we'll go over the good one. Now let's look at a better way of finding the speed of light. This one's a little bit more difficult to understand, but once we kind of get the hang of it, it's not so bad. Don't write anything yet, okay? I'm going to leave everything uncovered if you promise me that you're going to drop your pens and not write anything right now. Michelson performed an experiment that was somewhat more complicated, but somewhat dramatically more accurate, okay? Dramatically more accurate. He used 2 hills as well, but they weren't 1 kilometer away. They were 35 kilometers away. Now, that distance in itself isn't enough to make a significant difference. Well, it'd be 35 times more accurate, but still 35 times more accurate than absolutely terrible is just terrible. If you uncover the lanterns 35 kilometers away, you're still going to get really, really bad results. So he comes up with an even better way to find the speed of light using these hills that are 35 kilometers away. He's got over here, I'm going to describe this for the diagram and then you can go back to the description up here. He's got over here on this first hill, Mount Wilson, 35 kilometers away from the second hill, Mount San Antonio. He's got a light source. Okay? This light source is shone this way, you can see by this red beam here, at this rotating octagonally shaped object. Each side of this octagon has a mirror on it. So there's a mirror here, a mirror here, a mirror here, and so on. And it's rotating, they got it rotating clockwise here, although it doesn't really matter which way it's rotating, clockwise or counterclockwise. If the beam of light reflects off of that octagonal set of mirrors at just the right time, then it will reflect down here and come over here to Mount San Antonio and hit another mirror, a curved mirror, on this hill 35 kilometers away. If it doesn't hit it at just the right time, then what's going to happen? Let's say you're shining the light right here when maybe the face of that mirror, this face of the mirror, is oriented like this. What's going to happen to it? The light's going to reflect back here somewhere, right? If it hits it at just the right time, it's going to reflect down here to this curved set of mirrors down here, and then it's going to reflect back to this octagonal mirror again. If this octagonal mirror is in the right spot again as it's rotating, then this light will reflect off at the angle that we want it to reflect off of at. If it's not in the right place, then it's going to reflect off at some funny angle, up here or down here or whatever, and it's not going to be observed by the observer over here. So we need this octagonal set of mirrors to be in the right place twice for this beam. Does that make sense? If it's not in the right place twice, then this beam of light is never going to be detected by this observer over here. Okay? All right, so what do we do with that? Here's the crux of it right now. if this beam of light that's traveled this far down here to this curved mirror and then back up here to this octagonal set of mirrors reflects off of a flat side and gets observed by the observer, then we know that this octagonal set of mirrors must have made 1/8 of a revolution exactly, or 2/8 of a revolution exactly, or 3/8 of a revolution exactly, or 4/8 or 5/8 or 6/8 or whatever. Because if it didn't make exactly a whole number multiple of 1/8 of a revolution, then there's no way that the face of that mirror would be in the right place, and therefore that light would reflect off at some funny angle. Does that make sense? Let's focus on this one. Because what's really going to happen here is we're going to shine this light. We're going to start this mirror at rest, not moving, and then we're going to slowly increase the speed of it, slowly increase the frequency of it until the light gets observed by the observer. Once we find that this mirror, once we see the light at this observer over here, we know that we've reached the point at which this rotating mirror has made 1/8 of a revolution during the time that the light travels from this side of the mirror down here and then back there. Does that make sense? So we're starting this mirror at rest. Okay, what's going to happen when the mirror starts at rest? Well, of course, if the mirror is oriented the right way, if it's at rest, you're going to get light going from here, down here, back here, and it's going to be observed by the observer. But that doesn't help us out. Okay, if the mirror is not moving, it doesn't help us out at all. We're able to get a distance that the light's traveled, but that's about all we're able to get. If we start rotating it, we're all of a sudden going to find that this beam of light does not get observed by the observer. It gets observed somewhere else until it reaches the right frequency. When it reaches the right frequency, the light will get observed by the observer because that mirror will have made 1/8 of a revolution during that time. If we know that the mirror has made 1/8 of a revolution during that time, and we know the frequency of the mirror, how many hundreds of revolutions it's making per minute, then we're able to determine how long it took the light to travel that far. And we know the distance that it traveled 35 kilometers there and 35 kilometers back, 70 kilometers. If we know the distance that it traveled and by calculation the time that it took to travel that far, then we can calculate the speed using that old equation again, v is equal to d over t. This one gives us a much better value, a much better value. Why? Well, for two reasons. One, because the distance is actually 35 times what the distance was in Galileo's experiment, so that makes it 35 times more accurate. But here's the big thing, here's the crux of it. The timing device is much more accurate. We don't have a reaction time error here. Okay, if we know the frequency of revolution of this rotating mirrors, then we're able to get the time that it takes without worrying about starting and stopping the stopwatch, without worrying about uncovering a lantern. So reaction time is gone. Make sense? Okay, let's have you write this down, and then I'll show you mathematically how this ends up working. Ends up being not really that big of a deal, okay, once you see the mathematics of how you actually find the speed of light, okay? So write this down, and then we'll get into the math of it. All right, everyone, Daxon asked a question just a minute ago. He said, I still don't really get exactly where the time comes from. And I said, if you get the basics of this experiment, but you just don't get where the time comes from, just trust me on it that we can get the time, okay? Trust me on it for now, at least, that we can get the time. Daxon, in about 30 seconds, you're not going to have to be able to trust me anymore. You're going to know where the time comes from, okay? As long as we understand the whole idea of the 1/8 of a revolution and all that kind of jazz, the time kind of flows from that. And again, you'll see mathematically where that comes from in a second. We're going to do example 13.1 on page 650 now, which is going to answer that question for Daxon as well as a couple other questions here. It says a set of rotating mirrors in a Michelson experiment was rotating at 533 hertz. Okay? We know the frequency of these rotating mirrors. And the curved mirror was located at 35 kilometers away. Show how Michelson, I should say, determined the speed of light from this data. Show how he determined it. Let's just find it. Okay, let's just determine it. Okay, that'll show how he determined it. You are going to use two equations every time you see one of these Michelson problems. Every single time you'll use two equations, and it will be the same two equations every single time. There is nothing more recipe-based that we do in Physics 30 than this. There is nothing more do it this way every single time than this. Those two equations that we will always use are V is equal to delta D over delta T, or just V is equal to D over T, and T is equal to 1 over F. Both of those equations we've seen before in Physics 20. Constant velocity equation, and then T, the period equation, given the frequency. Got it? Always start with those two. Always. If I give you a quiz on this, and I will in a couple of days, okay, you can be guaranteed that you start this way. In fact, if you don't start this way, you should, I don't know what you should do. I don't know. Because I'm telling you, you got to do this. If you start some other way, then, I don't know, maybe go take grade 9 math or something. I'm not sure. Okay? You're going to do it this way every single time. V equals D over T, and T is equal to 1 over F. All right, let's start plugging numbers in. Okay, let's just start plugging numbers in and see what happens. We want to find the speed of light, so we don't know what V is. Do we know what D is? Yeah, we do. What is it? 70 kilometers, because the light travels 70 kilometers there and back. 35 kilometers there, 35 kilometers back, a total of 70 kilometers. We're going to convert that to meters, though, so it's going to be 70,000 meters. Do we know what the time is? No, we don't. That was Daxon's big question a couple minutes ago, right? I still don't get where we find the time. Well, here's where it's going to happen for us, Daxon. Let's go to the other equations to say I have two unknowns in the first equation. T is equal to 1 over F. T being the period, F being the frequency. T, the period, is 1 over the frequency. That's 1 over 533 hertz. What do we get for the value of big T there? 1 divided by 533. 0.001876 seconds. That's a really, really small period of time. We have just effectively measured the period, the time for one revolution of this rotating mirror, by just knowing the frequency. Now, it hasn't made an entire revolution. It's made 1/8 of a revolution. So what are we going to do with this time? We don't want the time for one revolution. We want the time for 1/8. What are we going to do with it? Let's divide it by 8. What do we get? 2.34 times 10 to the minus 4 seconds. That's going to be, we're not going to call that big T, we're going to call that little t. And I'm going to put a little subscript in there just to remind us that that's the time for 1/8 of a revolution. We know that the light traveled 70,000 meters during the time that the mirror made 1/8 of a revolution. So let's plug that value of little t now, t 1/8, into this equation. 2.34 times 10 to the negative 4 seconds. What do we get there? 2.98 times 10 to the e? That's pretty good, eh? 2.98 times 10 to the 8 meters per second. All we had to be able to do here is recognize when the light was observed by the observer. We knew that that would be 1/8 of revolution, and if we knew what the frequency of the rotating mirror was at that point, then we've just eliminated any kind of reaction time. Look at this. We got a time here of 2.34 times 10 to the negative 4 seconds. There is no way that you'd be able to measure that time physically by hand. No way. It's such a ridiculously small amount of time. But it is very conceivable to know the frequency of a mirror. Okay, how many revolutions per minute or how many revolutions per second that it's making. Okay, if we know the frequency, we can get the time by using the period equation. Daxon, does that make a little bit more sense? No? Okay, actually, let me just draw the diagram again here. Okay. So here's our 8-sided rotating mirror. By the way, you can see problems where it's not an 8-sided mirror. Maybe it's a 6-sided mirror, a 10-sided mirror, a 12-sided mirror. So pay attention to what it says, right? If it just says a Michelson experiment, it's safe to assume it's 8-sided because that's what he used. But it may say a Michelson-like experiment, where it's a 10-sided mirror. Pay attention to that. If that's the case, we're not going to divide by 8. We'll divide by 10, or whatever the case may be, right? Okay, we'll assume 8 sides here again. Okay, right now, this thing is stationary. We shine the light upon it. Okay, it's going to reflect this way down to the other hill, 35 kilometers away. Back up to this one. It's going to reflect off here. It's going to get detected. If this starts rotating, then this light is going to strike this side of the mirror. We'll call this side 1, side 2, side 3, side 4. It may strike side 1 of the mirror at the right angle, and it may bounce down here just like it did before, or it may not. It may strike it at a funny angle because side 1 may not be in the right place, okay, and it reflects it down this way. Okay, we're going to focus more on side 3 because that's the more important one. If it reflects back here when this mirror is rotating, then one of the sides of the mirror must be oriented like that. It's not going to be side 3 actually, because when this started, side 3 was right there. If it's rotating, then either side 2 or side 1 has to have come in to replace side 3. If it's going the lowest possible frequency to make this happen, then which side is it going to be that's gone in there to replace side 3? Side 2. So it's going to have traveled 1/8 of a revolution. If it travels anything other than 1/8 of a revolution, side 2 isn't going to be there. Side 2 is going to be maybe right here. If side 2 is right there, then the light's going to reflect down this way. Does that make sense? So light will reflect in many, many different directions unless the mirror is rotating at the right frequency so that you've got a side of the mirror in the right place to cause it to reflect that way. Okay, does that make some more sense? Okay. And as I said, that can happen. Side 2 can be in that place. Side 1 can be in that place. If side 2 is in that place, it's traveled 1/8 of a revolution. If side 1 is in that place, it's traveled 2/8 of a revolution. And that would still work, although our analysis would change slightly. We wouldn't divide by 8. We'd divide by 8 and then multiply by 2. Okay. No, it would give you the same value because the frequency would be different. So it would give you the same value for the speed of light. Bottom line is, though, okay, normally the way this experiment is done is you adjust it so the first time light is observed, the lowest frequency at which light is observed, is when you actually do the experiment, which will always give you the time for 1/8, not 2/8, but 1/8 of a revolution, or 1/16 or 1/12 or however many sides of the mirror is, right? Is that kind of okay? Yeah, we got some practice problems here, but do you want to do one more as an example? There's 3 of these. You know what? There's 3 of these. Let's do one of them as an example here, okay? Then there'll be 2 more practice problems, and then I've got 3 more on a little worksheet to give you as well, so that should be enough practice for you. Let's do question number 1 as an example here. Students using a 12-sided mirror. What am I going to tell you right now after I read that first sentence? Let's highlight 12-sided. Why do I want to highlight 12-sided? I didn't in the last question. I didn't highlight 8-sided or whatever. It didn't even say 8-sided. Why am I highlighting 12 sides? Because we usually use 8. How easy is it now if you're used to using an 8-sided mirror to just plug in 8 there? Okay, it's really easy. So highlight 12 just to draw attention to it. Similar to Michelson's experiment, the speed of light is found to be 2.88 times 10 to the 8 meters per second. So we're given the speed of light this time. The mirrors are 30 kilometers as opposed to our standard 35 kilometers away from the fixed mirror. What is the frequency of rotation if 1/12 of a rotation occurs before the light returns? So this time we're looking for F. Last time we were looking for V. This time we're looking for F. Doesn't change the way we start this. We know we have 2 equations that we're always going to use every single time. Every single time. V equals d over t, t equals 1 over f. Let's plug in numbers. Do we know what V is? Yeah, we do. We didn't before. We're trying to find it. This time we do know what it is. It's 2.88 times 10 to the 8. Do we know what d is? How far the light travels? What is it? 60 kilometers. Let's convert that to meters. We get 60,000 meters. We divide that by t. Look, we can find t. In the last example we did, we couldn't find t. We had to move over to the other equation. This time, right away, we can find the value of t. What is it? 60,000 divided by 2.88 times 10 to the 8. 2.0833 times 10 to the negative 4. What time is that? What have I really just found? The time for 1/12 of a revolution. So let's write that in as t 1/12. I can't put that into this equation because that big T is not the time for 1/12 of a revolution. It's the time for one revolution. So what do I got to do? Let's multiply it by 12. Remember in the last question you divide it by 8. This time you're multiplying by 12. That gives me big T. What's that? 12 times 2.08 times 10 to the negative 4. I'm sorry? 0.0025 seconds. Now we can plug that in here. 0.0025 seconds equals 1 over f, and then we can solve for f. F is equal to 1 over 0.0025. I think that's 400. And we're done. The same two equations, but solving for a different variable. Notice, though, in both of them, this will be a rule that always happens. It's always fulfilled. Notice in both of them. First question over here. The thing we found first, which was the time, is not what we wanted. The thing that we found first over here, which was the time, was not what we wanted. We're going to get a time. We're going to get a time. Each question we do, we're going to get a time first, but it's not the time you want. Okay, if you get little t, then multiply it by 8 or 12 or whatever the case may be to get big T, because that's the one we want. If you get big T, then divide it by 8 or 12 or whatever it is, because that's the time we want. You're going to get a time first, but it's not going to be the time you want, anytime. So let's either multiply it or divide it by 8 or 12 or 16 or whatever the case may be to get the time we want. And then let's plug it into the other equation and go from there. Is that okay? Once you get some practice of these guys, they become fairly straightforward, which is a good thing because since this became a part of the curriculum, I think it was 6 or 8 exams ago, there's been a question that's been effectively just like this, a straightforward Michelson experiment question. It's been on almost every single one of the tests, almost every single exam. Okay? So if we master it, and we will, then we should be able to get a gimme question on our test. Okay, let's see what we can do with question 2 and 3. And then if you're doing well on question 2 and 3 and you need more questions to work on, then I'll give you a 3-question worksheet. If you're not doing so well on it, then put up your hand and ask some questions. Right? Good question just asked by Nicole, guys. If you're not given the speed of light and you're not calculating the speed of light, if you're calculating a frequency, then you have to assume the speed of light is the accepted value of 3 times 10 to the 8. Okay? So if they're given a value that's other than 3 times 10 to the 8, they use it. If you're trying to find it, well, then don't assume it's 3 times 10 to the 8. Otherwise, you have to assume that it is 3 times 10 to the 8 if you're looking for something else like frequency.